Hello everyone, welcome to the InPathTES course number 3, topic number 7, Micro and Nanoscale Modeling of Thermal Energy Storage Materials. Welcome to our first lesson, Introduction to Micro and Nanoscale Modeling. In this lesson, you will learn the concept of multi-scale modeling and simulation, commonly used nanoscale and microscale models. Also, you will learn some preparatory knowledge of statistical mechanics and kinetic theory for the next lessons. In the introduction of thermal energy storage, you have learned the importance and challenges in material characterization and development. In this course, I'm going to introduce how to take a bottom-up approach to model thermal energy storage materials from the most fundamental laws of physics. At different scales, we have different angles of viewing a material. For thermal energy storage materials, as shown in this slide, we can have a heat storage tank at the meter scale, a macro-encapsulated PCM ball at centimeter scale, a carbon foam enhanced PCM at millimeter scale, a micro-encapsulated PCM at the micrometer scale, and a nanoparticle doped PCM at a nanometer scale. To study these materials, we need to model these materials at different scales. Additionally, many physical problems have important features at multiple scales of time and length. For example, in a sorption storage system, as shown in this slide, the physical phenomena at different scales influence with each other, and there is no unified theory can handle them all. At the reactor scale, the continuum model, such as finite element method, can be used to model the sorption reactor. As input, we need to know the water vapor pressure drop passing a unit length of the porous sorption material. However, this property is very much dependent on the tomographic structure of the porous sorption material. The porosity, the expansion in volume after sorption, and even the sorption-desorption history of the material itself. If you look at a smaller scale, at the powder scale, the pressure drop is actually coming from the water vapor passing through the gaps between the powder spheres. To better model and understand this, we can further go down to grain scale to study the nucleation and growth of the dehydration or hydration process on a single crystal. To understand the chemical reaction equilibrium and kinetics of hydration, we need to further go down to the molecular scale to study the multidimensional free energy landscape of a hydration process, or even go deeper into the subatomic scale to study the electric charge transfer and bond formation. The above approach to study multi-scale features and phenomena, either top-down or bottom-up, is called multi-scale modeling. In Wikipedia, multi-scale modeling is defined as follows. In engineering, mathematics, physics, chemistry, bioinformatics, computational biology, metrology, and computer science, multi-scale modeling, or multi-scale mathematics, is the field of solving problems which has important features at multiple scales of time or space. The definition itself includes part of the reasoning why we have to use multi-scale modeling method. First of all, the physical process of our interest involves features and phenomena at multiple time and length scales. In the previous example, electric charge transfer and bond formation influences the reaction kinetics of the sorption material, and the reaction kinetics then determines the nucleation and crystallization at the grain scale, and this then influences the correct formation and vapor flow in the porous material at the powder scale, which regulates the charging and discharging of the heat storage tank. There is no simple model to describe every phenomena in the above example throughout all the scales. Additionally, the limited computational resource forbids to simulate entire multi-scale problem using the most fundamental laws of physics, for example, using molecular simulation. Models, simulations, and experiments are indispensable to each other. Experiments give observations, models and theories explain observations, and through simulations and calculations, we predict observations. Simulation can sometimes replace experiments when experiments are practically impossible. Additionally, we can have a high degree of control of variables at one time when doing simulations. But we have to be aware of the applicability and the assumptions made during the simulations. And we should be aware at what time and length scale the simulation works. In this multi-scale hierarchical approach, the models and simulations are built upon each other. In this schematic diagram, a few models and simulation methods are given. At the subatomic scale, we can study the electronic structure of an atom or a molecule. This is also the scale quantum mechanics works. Going up in the ladder, we come to molecular dynamics. In a molecular dynamics simulation, each atom is built explicitly with its own mass and charge. There are ab initio MD, which is closer to the fundamentals, classical MD, which features Newtonian dynamics, and various accelerated MD methods using stochastic dynamics, Brownian dynamics, coarse graining, steering, and so on. Further up comes the Monte Carlo methods. These methods directly sample the phase space of a system and are therefore much faster. If we keep going up in the multi-scale ladder, we can no longer simulate a system with explicit atoms. Instead, the degrees of freedom in the system must be simplified by considering millions of atoms as a segment. There are two examples given: the phase field model, which deals phase change and interfacial systems, and the lattice-Boltzmann methods, which studies the fluid flow and transport phenomena using discrete Boltzmann equation. Finally, we get to the continuum scale. The most commonly used method here is the finite element analysis, which studies a system by its elements and ignores the physical details within an element. In this lesson and the following lessons, we will learn how to model and study a thermal energy storage material at the micro and nano scale. This includes the density functional theory, molecular dynamics, Monte Carlo methods, and lattice-Boltzmann methods.